Standard local search algorithms follow a rigid logic. They only accept improving moves, rolling downhill until they can't anymore. If the path bottoms out in a shallow valley, the algorithm stops, completely missing the true lowest point further down the board. To break out of that trap, an optimization model needs two structural capabilities. First, it must be allowed to travel uphill by accepting moves that temporarily worsen the solution. Second, it requires a mechanism to prevent it from immediately sliding backward into the exact same valley it just left. If a problem is unimodal, meaning its search space consists of a single smooth slope with exactly one minimum, standard local search works perfectly. There are no false valleys to get stuck in, so uphill movement is unnecessary. But real-world optimization models feature high-dimensional, rugged landscapes packed with local minima. Navigating them requires metaheuristics, like Iterative Local Search and Tabu Search, that force the algorithm into unexplored territory. Iterative Local Search, or ILS, tackles local minima without maintaining a history of the search space. When the algorithm hits a dead end, it relies on a brute force mechanism known as perturbation. Perturbation operates like a random kick. It forcefully displaces the current solution, launching it far enough to clear the local valley and drop into a completely different region of the graph. Once the solution lands, the algorithm resumes its standard local search. It evaluates the new immediate neighbors and rolls downhill until it settles into a new local minimum. Because it only tracks the current and best solutions, ILS is highly memory efficient. The trade-off is that a random kick has no sense of direction. It risks sending the search directly back into a valley it has already fully mapped out. Tabu search takes a more methodical approach. Instead of kicking the solution, it actively climbs out of the valley by systematically accepting worsening moves, taking calculated steps uphill. To prevent the search from immediately sliding back down, Tabu search uses short-term memory called a tabu list. As the algorithm moves forward, it logs the recent path, effectively dropping a barrier behind itself, so those specific moves become forbidden. To save computational resources, the tabu list does not store the massive data footprint of an entire previous solution. It only records specific attributes or individual variable changes. These barriers are temporary. Each forbidden move is governed by a tabu tenure, a strict time limit on how long it remains blocked. Once a move exceeds its tenure, it drops off the list and the path opens up for exploration again. The algorithm also deploys an aspiration criterion. If a forbidden move leads directly to a solution that is measurably better than the best solution found so far, the algorithm overrides the tabu list and crosses the barrier. By trading memory storage for precise control, Tabu search builds a moving wall. It actively blocks repetitive cycles, forcing the algorithm away from dead ends and into productive new space. Let's apply this to a max-sat optimization problem. Candidate solutions are binary strings, and we move by flipping a single bit. Our current solution is 101100. The tabu list array below it tracks exactly when each bit index was last flipped. Assume our tabu tenure is 2 iterations. Pause the video and determine which of these 3 single-bit flip neighbors are currently forbidden and which one represents a valid move. The first and third bits were flipped too recently. Reverting them creates an immediate cycle, so the tabu list blocks them. This leaves the second bit flip as our only permitted path forward. By intentionally invalidating accessible neighbors based on recent history, the tabu list shapes the geometry of the search space, steering the processing power exactly where it needs to go. Choosing between these algorithms depends entirely on your problem space. If your task features structured, repetitive constraints, like the vehicle routing problem, Tabu Search's methodical memory is the optimal fit. Conversely, iterated local search works best in domains where small, randomized perturbations easily break existing structures, yielding high-quality starting points without the overhead of tracking complex memory. To sum up, iterated local search relies on blind perturbation to forcefully escape local optima while remaining memoryless. Tabu search deploys structured, temporary memory arrays to walk itself out of valleys without repeating steps. Save this summary matrix to assist in identifying the right metaheuristic for your next optimization framework.